Hi all, welcome to another video of linear regression. So in the previous video we have seen what is a simple linear regression. Okay, so what is a simple linear regression? In simple linear regression, the dependent variable y is a function of a single independent variable. So in this case the predicted value can be written as beta naught plus beta 1 x. For example, we can write the weight of a person, that is a function of height. So that will be given by beta naught plus beta 1 times height. Okay. So this beta naught and beta 1 are the intercepts and the slope values. So beta 1 slope and beta naught is the intercept value that we are actually getting. It's directly, we get it from the machine itself. We don't have to calculate it mathematically. We get it from the machine itself. So then the next type of linear regression we have just started with, that is multiple linear regression. Next type is multiple linear regression. Actually, in the practical world, we don't have a simple linear regression. Even if we are talking about this example, weight of a person is directly proportional to height, there can be many other factors affecting the weight. So practically, we don't have much examples of simple linear regression. Most of the practical scenarios that is actually a type of multiple linear regression. So we can write, in this case, we can write y is a function of different independent variables, x1, x2, x3, x4, etc. All these variables. And this can be the predicted value y predicted can be written as beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Like this, it goes on. That is, for example, we are writing the price of a house. The price of a house can be written as what? Beta naught. It can be a numerical value plus beta 1, another value, times area of the house. Like that it goes on. But while going into detail, the multiple linear regression, we can see in the case of multiple linear regression, there can be, for example, the price of a house. It can be affected by many other factors like area. Then it can be the number of bedrooms. Okay. Then beta 3 x3 can be the number of bathrooms. But there can be situations where this x can be a categorical variable. That is, it can be x4, can be location. So here we can see, can we multiply beta naught, beta 1, beta 2, it can be any value. So we can write beta naught is equal to 0.5, beta 1 is 1.2, beta 2 is some other value, 0.7, something like that. We are getting this value directly by running our Python code. Okay, we can see how we are getting this value using Python code, that we can see in the coming session. But for now, you just check beta naught 0.5, that's fine. 1.2, beta 1 is 1.2 times area, that is fine. But you can see if beta 4 is having a value, can we multiply that number to the location? Location can be any place, right? Location can be, for example, we can say location of a house. It can be places like place A, place B, place C, like that. So we can't multiply a numerical value with a location, right? These locations, they come under the categorical variables. So it's not practical, it's not possible to multiply a number with this type of categorical variables. So here comes the concept of dummy variables in linear regression. Here comes the concept of dummy variables. So dummy variables, I will just write the example here. The price of a house, that depends on the area, then the number of bedrooms, and we can write the next variable as the location. Okay. So we can first find our data. Price of a house, let it be 50. The area can be, let it be 1000, 2, and the location is A. Next is 60, 500, 3, location be B. Then for 55, let it be 1100. The number of bedrooms is 2 and the location is again A. So for our convenience, we are just taking only 2 locations. So when you are converting it into dummy variables, all these three, price, area and bedrooms remain as such. The price, area, number of bedrooms remain as such. The location will become location underscore A and location underscore B. So here you can say this location of this house is at A. So here it will be 1 and here it will be 0. And here in this case this will be 0 and this will be 1. Here also this will be 1 and location B will be 0. This is the concept of dummy variable. So that is, we are encoding it binary. This is also known as one-hot encoding, but the difference between dummy variables and one-hot encoding is that in the case of dummy variables, we need, that means if we have n variables, n categorical variables, we need n minus 1 columns in the case of dummy variables. That is, for example, we can see here we have 2 categorical variables, A and B. So even if we consider only location A, that will be fine. Wherever we have 0 for location A, by default, it can be to the other unique variable, right? So this is known as dummy variables. And if you are taking if you are taking the number of columns as same number of variables, that is known as one-hot encoding. Okay, so I can just explain the concept of dummy variables again. This is important. So you can see the price of a house. It can be dependent on many factors like area, number of bedrooms, number of bathrooms, location of the house, etc. So if you are finding the coefficients, the intercepts and the coefficients using the Python code, we will get some mathematical values and we can multiply that mathematical values with area, bedrooms, number of bathrooms, etc. But it's not possible to multiply a number with a location given or any categorical variables. The location we can see, we are taking, for example, we are taking the locations at A, B and C. And here comes the importance of dummy variables. We are assigning a dummy variables, or we are dummy variables to this categorical variables, binary variables, or we are converting this categorical variables into binary variables. So if we have three categorical variables, we can use two binary variables to denote that. That is, here you can see, here in this example we have taken only A and B as the unique locations. So we can write location A and location B, and wherever it's the location A we can put 1, the other way it will be 0. This way of assigning categorical variables as binary numbers, that is known as dummy variables. If you are taking the same number of variables and the same number of columns, that is one-hot encoding, and if you are reducing the number of columns by 1, we are calling it by the name dummy variables. Okay. In linear regression, this dummy variable creation, that is actually mandatory. Otherwise, dummy variable trap may occur. So that is dummy variable trap, that is multiplying number with categorical variables. It can result in dummy variable trap, and the problem is that the equations in the previous classes we have seen, we are taking the derivative, finding the minimum of the function, minimizing the error, taking the derivative to find beta naught and beta 1. See, so we won't be able to solve those equations and the equations will become indeterminate. So you might have heard about indeterminate equation. We cannot solve it. That is, dummy variable trap occurs. If we are not assigning dummy variables, the equation will become indeterminate. Okay, so that's why dummy variable creation is actually mandatory, especially in the case of linear regression. Okay, and also we can see in the case of linear regression, we are getting the equation like this: beta naught plus beta 1 x1 and beta 2 x2, like that it goes on. We will get values, we will get numerical values for this beta 1, beta naught, beta 1 and beta 2, and this is the main property of linear regression. That is, we can see whether all these parameters are positively or negatively affecting our prediction. Positively or negatively, that means we can have the beta naught, beta 1, beta 2, it can be either positive or negative. These values can be positive or negative. If it's positive, we can say it's positively. That means the predicted value is increasing if beta 1 is positive, and it's decreasing if it's negative. Whether it is positively or negatively affecting our prediction, that is clearly visible from linear regression. In other algorithms that we are going to see in the coming classes, we don't have any idea about these coefficients and their values. Okay, and also if we have 1,000 rows, if we have 1,000 rows of data, 1,000 rows of data, we are splitting this 1,000 rows into 2. That is 800 rows we are used for testing. So if 800 rows we are used for training, and the remaining 200 rows we are using it for testing. So that is, we can see in detail that one. Here you can see we have 1,000 rows. We have 1,000 rows of data. We have the house prediction, the house price Y, and the other factors affecting areas, number of bedrooms, number of bathrooms, the location, etc. are here. And here you can see, here we have 800 rows, and here we have our 200 rows. We know all these values we know. The price, the area, bedroom, bathrooms, all those parameters we know. And using this 800 rows, we are training our machine learning model. This 200 rows is for the test data. That is, our machine learning model is trained only on this 800 rows of data, and the model hasn't seen 200 rows of data. That is, that data is a new data or unseen data for our machine learning model. After training on 800 rows of data, we are developing a function, or we are finding a function f to model the price of the house. Price of the house, that is equal to a function of area, number of bedrooms, number of bathrooms, the location, swimming pool. Using all those independent variables, we are finding a function to predict the price of the house. And this function we are testing on. This function we are testing on the remaining 200 rows to predict the price. The predicted price, that will be the same function. The same function we are applying on the remaining 200 rows of data. But the thing is that we actually know the actual price of this 200 rows, that we already know. So we have that price, and we actually know the price, and we are predicting the price using the function v model. And using this actual price and predicted price, these prices we are used to evaluate the efficiency of our model. So we are trying to reduce the error. So we are going to see in detail different errors that can occur here. That is root mean square error, mean absolute percentage error. All these errors we are going to see. This we are finding out by taking the difference, or by evaluating the actual price as well as the predicted price. By taking the difference or evaluating in different ways, we are trying to improve the efficiency or reduce the error. Okay. So we can see in detail what are the errors and how to calculate the efficiency of a model in the coming session. Okay. Thank you.